Again, good morning and welcome to today is actually April 1st. This is Physical Science 1, of course, and Thursday. So let's get started. Today, the chapter is going to be on atomic and nuclear physics, basically, and radioactivity. It's the stuff that is inside, basically, the atom. I know we did a little bit of atomic physics a little bit before, in a sense that is on the atomic scale and things like that, basically for the atoms and the periodic table and things of this nature. Now we're getting deeper and deeper, so we are well inside, basically, the inside the atom. More specifically, we're going to go inside the nucleus. These distances are extremely small. I mean, of the order of what is known as a femtometer. Femtometer is 10 to the negative 15 meters, extremely small sizes. Okay, so that is where the nucleus is, and that is where a lot of the action is happening in terms of basically stability of matter in general. So this is what we're going to be talking about. So let me share the screen. Okay, again, this is the topic of the day. This is the stuff we'll be covering today. Is radioactivity is one of the natural phenomenon that happen on their own, and it's a force by itself, basically, that causes this this behavior where materials all of a sudden emit energy in the form of particle moving, or in the form actually of pure energy in the form of electromagnetic radiation. So this is basically what radioactivity is. The first thing that I must say, it has nothing to do with human activity. It has existed, as a matter of fact, before humans, number one. Number two also is that without it, actually, life would not probably have prospered on Earth at all, because it's at the core of the Earth, and it's really what heats the Earth and causes core to be molten. And in a sense, that is really the essence of how currents are inside the Earth to generate the strong magnetic field that the Earth has, to protect it, among other things, particles that come from the cosmos and the sun and everything else. So that's basically, so it's, in a sense, it's a positive thing, not necessarily a bad thing. Case in point, for example, if you take Mars is so small that most of its radioactive, basically, materials, at least it's not as radioactive as the Earth, at least that's what we believe. And its core is not really does not have a lot of currents in it as much as like the Earth does, because it's not hot enough. In terms of speed, Mars spins as fast as the Earth does. So if it has currents inside, it should really have I mean, if it's molten inside as much as the Earth is, it really should have currents, and it should have strong magnetic field, but it doesn't. So that is really why we're thinking what's going on. The case for Venus, it's the opposite of the side, because the problem with Venus, although we believe it has the same core temperature as the Earth does, but it doesn't spin as fast, spins so slowly, so there is not enough probably currents in it to generate the magnetic field again. So that's basically, in a nutshell, what's going on with radioactivity. So radioactivity is an important thing for life on Earth. The atomic nucleus and the strong nuclear force, basically, we will see that, look, with the exception of hydrogen atom, all of the other atoms or the elements, they have inside of them 2 protons or more. So if you take a proton which is positively charged and another proton that is positively charged, they really don't want to be next to one another. They repel one another because both of them have the same sign, the same positive charge, because of the electrostatic force. Electricity will make it so that positive charges will repel each other, and this would lead ultimately to the rip-off of basically no single nucleus could exist, with the exception of hydrogen, because that's the only one that has only single proton in it. So to explain what's going on in here, we must have a force that is stronger than the electrostatic force. In other words, a force which we call it the nuclear force, that at some point, even though both of them, they don't want to be next to one another, the nuclear force takes over and actually fuse them. Okay, so the nuclear force is stronger than the electrostatic repulsion, by a huge factor, as a matter of fact. I mean, by more than 100 times more stronger. So that's why we call it the strong nuclear force. We call it strong nuclear force because it is the strongest force that we can think of, or we know, at least in nature. So a proton and a proton, when they get next to one another, they will be attracting one another. However, because of that nagging issue with the charge being still there, in a sense, there is a repulsion still. So this is really not very, very strong. If, in case, what I do in this case is, if I bring another element that does not have a charge, neutral, but also can solidify and strengthen that bond, then that's great. And that is the role actually of the neutrons. So the role of the neutrons is to make that bonding even stronger. And that is really how the nucleus is held together. Obviously, this is fine and good as long as I have enough protons added together. The minute I add more, I have enough neutron added together, the more protons I do add. And that will keep the atoms or the nucleus more and more stable up to a certain point. When it grows beyond a certain size, then in this case, the proton on one side and the proton on the other side, they're too far away to be held together with the nuclear force, but they are close enough for them to be repelled with the electrostatic force. So in other words, the nucleus becomes unstable. That's why there is a limit to the size of all of the elements. We cannot really have more than a little over 100 elements in nature. Because if you want to add more to make the atom bigger and bigger and bigger, you have to bring more protons. And in order to make those protons stick to one another, you have to bring more neutrons. No matter how many you bring at this point, you have a size that is too huge for the nucleus, that this proton and that proton on each side, and this proton and that proton on the other side, they will be too far apart for the nuclear force to hold them together, but too close for the electrostatic to really repel them, because the peculiarity with the strong nuclear force is really a choosy force. And like the electrostatic force, named Coulomb's force, which doesn't care. As long as you have two charges, if they are of the same size, they will interact no matter how far they are. But the strong nuclear force is picky on the distance. It only matters for it when they are too close. If they are too far, it says, forget it. I'm not going to bother with that. So that's what's going on in here. Then we're going to introduce the concept of half-life and retransmutation, basically a transformation of a material, an element from one type of element to a different type altogether. Completely different materials. So this is basically what the idea in here is. And the half-life plays a major role in dating materials, whether on a small scale or on the large scale. Obviously, this has to do with the little bit of how the process starts, but that's basically what we use them for, and that is exactly radiometric dating, which is used for dating materials, whether of organic nature or of different fashion. And then we're going to talk about the energy fission, and in the case of two nucleon, whether being a proton or proton or proton and neutron or neutron and neutron, they come together. They have to lose some energy, and that energy is exactly what is needed to bond them together, okay? And that is given by this expression, E equals to mc squared. So the loss of energy is actually coming from that expression, and that is the bonding, actually. So when they fuse together, they're bound together. Now, if you put a bunch of them together, and there is a lot of them together, there is a lot of loss of energy in this case. If somehow you break them apart, you release that energy out of them. As a matter of fact, if you bring them together, for the case of the nuclear fusion, there is also, when they come together, they lose energy, and that is the energy that comes into bonding. This is true from both sides of the spectrum. For the light elements, you can fuse them to make heavier and heavier elements. And for the extremely heavy elements, you can actually break them apart in fission and bring them also to smaller elements. There is a point in the curve where you cannot do anything about it. That is the absolute minimum energy per nucleon, and that is the case of iron. So iron is the most stable nucleon there is, because of the fact that at that point, you cannot go any way, whether on the heavy side by fusing more and more, or on the light side by breaking more and more. So that is basically the most stable of the configuration. As a matter of fact, iron is dubbed the, when a star basically starts, because stars make elements all the time by fusing elements together. Starts with hydrogen, mixing with another hydrogen, and actually 4 hydrogen basically coming together and making an element of helium, and then helium and other helium combine together, making other elements, and they go through all of the process. Depending on how big the star is, it can start making elements like carbon, oxygen, nitrogen, and starts making heavier and heavier elements. Like, for example, for our sun, it's going to make carbon and oxygen and all of that at some point in its life down the road. But more massive stars, actually, they can start making even heavier elements. Now, the problem with it is that once they start making iron, they cannot make any more. They're stuck in iron. And the process becomes too fast for them. And once they make the iron, basically, that's when they start to go into an unstable configuration and actually go to supernova. During that stage, they make the other elements after that. Anyway, so that's why when a star makes an iron, it really has signed its own death. Okay, that's it. It's going to go supernova immediately there is. And that is coming from this process, from this understanding of what's going on in here. So radioactivity results from radioactive decay, which is the process whereby unstable atomic nuclei transform and emit radiation. Again, as I said before, nuclei can be stable. Like, for example, if I take helium, the nucleus of it, which is called also the alpha particle, that is a stable configuration. It's not going anywhere, okay? But if I start fusing more and more protons and neutrons, at some point there is an imbalance in terms of the energy, and the nucleus goes into getting rid of that excess energy, and it gets rid of it through this process, which is called radioactivity in this case. Okay, and it has existed before humans. So I know that there are some politicians out there, and probably some people from one side or the other side of the aisle, who blame somehow everything on human activity. This is not one of them. Radioactivity has existed before, okay? It has nothing to do with the nuclear bomb or anything like that. It has existed before that. So, okay. So unstable nuclei have an imbalance of neutrons to protons, and they become radioactive. So that is basically what, in a nutshell, what that is. It exists everywhere, not just in Earth. I mean, if you go to Venus right now, it has a lot of radio. As a matter of fact, everywhere there is matter, which has radioactivity in there. Okay. Most radiation, though, for the vast majority of the radiation, is of a natural background, come from cosmic radiation, where from the sun or the rest of the cosmos, or actually from the Earth itself. Earth itself has a lot of materials that are radioactive. Okay, if you go higher and higher in altitude, obviously you're exposing yourself more and more to more cosmic radiation. So there are two types of cosmic radiation. There are particles, mainly two types of particles, so-called alpha particles and beta particles. And those, they have mass. That's what we mean by particle. So the word particle in here has to do with mass. And this is massless radiation. This is pure energy. This is EM waves. And this is mainly the nucleon of helium or or electrons. Okay. Obviously, helium in here is super heavy compared to an electron, but both of them have mass. Okay. So that is basically in a nutshell what this thing is. So this is the natural radioactivity that we talk about on a regular basis. They affect us indirectly, of course, because look, we have nitrogen in the atmosphere, okay, N2. That's the gas. That's the main gas in the atmosphere. What you're breathing right now is not really oxygen. You're breathing for the vast majority nitrogen. Of course, your body doesn't do anything with it, gets rid of it immediately, at least through the breathing. But the oxygen is the one that is extracted from there, and it actually makes about a quarter of the other one. But nitrogen is abundant in the atmosphere. So what it does in here is this radiation that comes from the atmosphere hits it, and in doing so, it converts it from nitrogen to carbon 14. Carbon 14 is not really stable, okay? Carbon 14 is not stable, so it decays automatically to carbon 12. And this is a process through which we can carbon date materials, basically. This is how we know it. So on a regular basis, on a regular event, for example, on a regular year, there is always carbon 14 in the atmosphere that is being continuously created by this transformation from nitrogen to carbon. This is, I meant with it the molecule. It's not that it has two atoms, okay? Two nucleides. Okay. It converts nitrogen to carbon, and the carbon goes to another other form of carbon, the regular form that we know. But there is a balance in here on a regular basis. So that's basically what we have. And materials like especially the plants, they take the carbon, both forms, and if you examine them when they are alive, there is a certain proportion that is really related to this activity, okay? Obviously, once the plant dies or it's consumed, at that point, it's not going to be taking any more carbon. So whatever carbon it has in it, especially carbon 14, is going to decay and transform on its own to carbon 12. So if I have a sample now of a dead plant, or an animal that took that dead plant, ate it, then in this case, what I can do in here is find how many carbon 14 is left versus how much carbon 12 is in it. Based on that, and based on the lifetime of this process, I can tell how old this one is. Isn't this fascinating? I mean, when plants die, they don't tell us when they died, but we can find out. It's like forensic science, okay? That's exactly what is used in here. So the origins of carbon go back to what? To the military activities of the 20th century, or to the Industrial Revolution of 2 centuries ago, or the beginning of the human era? That's a good thing. That's a good guess. What is the beginning of the human era? What is that? Can anybody tell me what that means? Obviously, the correct answer is this one, okay? It's D. But I'm wondering what is the beginning of the human era? I don't know, okay? I can tell you when it started with me. It started when I missed a goal a few years back. So that's, I think, my, I should have scored it. Anyway, so it's just for fun in here. I don't know what that means, okay? I know probably it may go to some sort of religious belief or something like that, but that's not the case in here. So anyway, so the correct answer is before humans emerged on Earth. So it existed before that, before any human activity or any politician or anything like that, okay? So when an atom undergoes into a radioactive decay, it becomes an ion of the same element? Not necessarily. Actually, it has nothing to do with ionization. It's inside the nucleus, what's going on in here. Becomes an isotope of the same element, turns into a completely different element, may or may not turn into a completely different element. I think this is the correct answer is D in here. Why do I have it as C? It depends on what type of radioactivity we're talking about. If it is an alpha, then you're talking about C. If it's a beta, then you're talking about C. But if it's a gamma, then the element does not even change. It says the same thing. Okay? So the correct answer should be D. Most of the time it's C though. So here is the three types that I was talking about, okay? The alpha decay, the beta decay, and the gamma decay, okay? And the way we can tell about them is putting the radioactive materials, for example, lead in this case, next to a magnetic field and see which way the particles go. If it has one type of a charge, it's going to go one way because it's deflected by the magnetic field one way. If it has the other charge, it's going to be deflected in the opposite direction. This one has no charge. This one charge of it is 0. That is pure energy. So that is how we can tell which one is which. Furthermore, depending on the mass, we can also tell, depending first of all on the strength of the charge, we can tell by how much it's going to turn, to tilt. Because the more charge, the more bending you're going to have inside the magnetic field. And also depending on the inertia, the mass. This one has less mass, so the magnetic field has an easy way for it to bend it. Whereas this one is a lot more mass. As a matter of fact, it's about what, 8,000 times the electron, because it has 4 protons, 4 nucleons. So in this case, it's far more massive. So it's going to have more inertia. So the combination of this, you can tell the types for this ones. Just put them through a magnetic field, and you can find a lot about their properties. Okay. So again, alpha particles consist of two protons and 2 neutrons, which is essentially helium, a nucleus, the nucleus of the helium atom. That's exactly what it is. You have 2 protons. You have 2 neutrons. This one have positive charge. This one has positive charge. This is neutral, and this is neutral, and this is what the alpha particle is. Okay. Loses energy quickly during interaction because it's a supermassive object. It has a very large mass, so you can stop it really easily. And it interacts with matter easily, so that's why a piece of paper, you should be able to protect yourself with a piece of clothing. You should be able to protect yourself from the alpha particles. Alpha particles, they does not normally penetrate lightweight materials, paper or clothing, causes significant damage to the surface of a material, living tissue, to the surface, burn on top of the surface, okay? Due to great kinetic energy, because it hits it, yes, it's going to be stopped, but it's going to lose that kinetic energy and cause damage to the surface. And picks up electrons and becomes neutral, basically. So actually, the alpha particle, when it comes from the nucleus, immediately after it's ionized, basically a helium atom, because this is exactly what this is. Okay. Then the minute it encounters an electron here and there, it's going to grab them and becomes neutral helium. End of the story. So it becomes exactly a helium atom. So, and at the end travels in the air and becomes just helium, just regular helium. It's deflected in the presence of the magnetic field because of these 2 charges. Beta particles, on the other hand, is an ejected electron from neutrons. So basically what's going on inside, that we know at least how the theory of it is, you have a neutron. So when the neutron basically transforms itself to a positive proton and then an electron, negative charge. So if you add up the 2 charges, this nuclear reaction conserves charge, because you started with no charge and you ended up with +1 charge and -1 charge, which is still no charge. Okay, so there is conservation of charge in here. So that's why the mass of the proton, of the neutron by itself, is slightly bigger than that of the proton. By how much? By this much, the mass of the electron. Actually, that's slightly less than that. If you add these two, they're slightly more than this one, because, but it's still, you can account for the difference in mass via the energy that bound this neutron. But it's still, neutron has both of them, it seems like, in it. And that's how we get beta. This is called the beta particle, or beta decay. And this is how the beta decay happens in here. So a material inside, it has an atomic number, a given atomic number. If it goes through a beta decay, that atomic number increases by 1. Because the number of protons inside the nucleus changed from whatever it was to this new number plus 1, because one of the neutrons now became a proton. So it goes completely to a different element. Same thing, by the way, in this case in here. This atom that went through an alpha decay, what happened to it before in here, it has a Z number. Now this Z number would decrease by 2 because it lost 2 protons in the process. And the Z number in here, the atomic number, counts how many protons you have. So if you have, I don't know, let's say, for example, you have 80, you lost 2, now you're going to be left with 78 protons inside. So this is a different material with a different Z number, with different atomic number. But for this one, for the beta decay, it's the other way around. Oops, what happened? For the beta decay in here, what happened? And let's say, for example, you start with 80, and now one of the neutrons became a proton. So now you end up with 81, because an electron was ejected. So an electron is gone, so that carries with it 1 charge. So it's still conservation of charge, but the element by itself left that was 80 now has been promoted to the right in the periodic table. So if you look at the periodic table, here is the periodic table. Here's the element that we're talking about. I'm just taking an element Z in here. If it goes through a beta decay, it goes from Z to Z plus 1. It moves to the right by 1 step in the periodic table. Whereas if it goes through a beta decay, it's going to jump by 2 steps backward. So it's going to be here at Z minus 2. Okay. So in this case, this is the alpha, this is the beta decay. And in this case, it's actually an alpha decay. So it's going to move to the left in the periodic table. Left 2 steps from what it was. Okay. That's why you have different element altogether, different material altogether for alpha and beta decay. Okay. Obviously, it has a smaller mass. The beta particle has smaller mass because it's an electron, actually. Loses energy at slower rate because it has a lot less mass in this case. Can be stopped by several sheets of aluminum foil. So you cannot really do it with one, so you have to have a long number of sheets in there to slow it down. For example, in a nuclear reactor, we sometimes have to deal with this type of particles too. They come out from the nuclear reactions in there. Okay, penetrates fairly deep into skin, potential for harming or killing living cells. So it really could do a little bit of damage in here. Once stopped, becomes an ordinary electron, just floating in there, whatever it is. It's captured usually most of the times by atoms. Is deflected into the opposite direction of the alpha particle because it has a different sign. It's a negative sign. Okay. What we're talking about in here is the natural, the normal, basically, occurrence of radioactivity. In a nuclear reactor, you might have some of these elements coming out, okay, and probably others too. Like, for example, in a nuclear reactor or actually a nuclear accelerator, you might end up with even another type of electrons that have the same charge, the same mass, the same property, except that they come out positive, with a positive charge. So that's a different process. We're not talking about that. We're talking about this natural processes. So you start up with an element Z. If it goes through a beta decay, it moves to the left in the periodic table. Okay. If it goes through a beta decay, it goes to the right in the periodic table. So this is what I want you guys to think about in terms of the transmutation of materials and how they transform. Okay, So this is the item that I want you to talk about in here. If it goes through a gamma decay, in this case, it's not going to change in the periodic table. It stays what it is. Okay, makes sense?
So you just want us to list the different decays for alpha?
For the alpha and the beta, and what it means for the element on the periodic table, which way it goes, this way or that way. Okay. Gamma rays are high frequency electromagnetic radiation, are emitted when a nucleus in an excited state moves to a lower energy state, and are more harmful than the alpha or beta particles, are most penetrating because they have no mass, are pure energy, greater per photon than invisible or ultraviolet or even X-rays. So these things are dangerous, okay? Their frequencies are the order of 10 to the power 20 to the 10 to the power 24 hertz. So it's really a lot, okay? Are unaffected by magnetic and electric field and therefore interact via direct hit with an atom. So when they go through a material, they don't, an electron does not do anything to them. So an electron is not going to absorb a gamma ray and move around up and down because it's too much energy for it, and it's not the energy that is going to correspond to any energy level transition for it. So going to go straight to the nucleus and affect the nucleus. That is where it's going to be absorbed. So it's really a very, very high energetic thing that can cause a lot of damage if it's absorbed by the nucleus. Okay. Gamma rays are super, super energetic things, and they're actually part of the cosmic array of particles that we receive on a regular basis. Again, we call them particles because they are photons, actually. They are particles just, as a matter of fact, as much as any visible light is, or any frequency is. But they're essentially EM waves. By the way, this is actually a follow-up to the same discussion point in here. You're going to state the fact that the gamma ray, the decay is normal electromagnetic, because you need to list all three of them, radiation. With the exception that it's extreme with extreme energy, high energy. So it's not like any other normal electromagnetic radiation. It's not like red light, for example, or blue light, or ultraviolet light, for example, or even X-ray light, for example. This stuff is super energetic, okay? So which of this is the nucleus of the helium atom? Of course, alpha particles. So here is the deal with the nuclear force, as I was talking about in the beginning. If the particles are close from one another, this is very, very, very strong nuclear reaction. I mean, very strong force. It attracts. The nuclear force is always attractive, though. Always attractive. It doesn't matter if you are an electron, I mean, if you are a proton or a neutron, you play the game. You are in. You're allowed into this game. Okay? So if the two of them are very close from one another, you can clearly see that it overpowers this force, which is due to the electrostatic force. This one says that if you have a positive charge and another positive charge, they repel one another. They don't want to be near one another. They push each other opposite direction, okay? But this is its strength. Compare that to the strength of the nuclear force. So in this case, there is an attraction. There is a net attraction. There is a repulsion due to Coulomb force, but there is an even more attraction due to the nuclear force. So in this case, they stay in one another. You push them slightly away, this drops back to almost practically zero. And this, because of now that they are far away than what they were before in here. It also drops, but not that much. So now you have a net repulsion. In this case, you have a net repulsion. If they're just enough away from one another. If they're just enough close from one another, you have actually a net attraction. Okay, so here is the deal. When they're too far apart, there is still some tiny remnants of that attraction, but there is actually a repulsion. When you bring them closer, the repulsion becomes even more. So you really need to work very hard to overcome that last breath, if you wish. Once you do that, then the attraction will take over and bring them closer. And albeit it's still hindered by this still present repulsion, because you still have, this never stops. It's always there, no matter how far you are. This one practically stops when they are far away. Okay, practically there is no nuclear attraction between them. Okay, so this explains the balance inside the nucleus. These two forces is what really makes a nucleus the way it is. So this is what makes all the different elements. This is an essential interaction between these two forces, the strong nuclear attractive force versus that of the repulsive electrostatic force. Okay, that is really the balance between the two forces. Obviously, this will be helped dramatically if I bring more glue, because these are glued now due to nuclear forces. But if I bring more protons, actually, it's going to make the situation, it's going to improve the situation a lot. Okay, so that's going on. That's what's going on. So the strong force is a force in the atom that holds electrons in orbit. No. Nucleus that holds nucleons together, absolutely. That's the only correct answer in here. Okay. Because what holds the atom together in the electrons in orbit is actually the electrostatic force. So this one, the other one. That's really what is responsible for the atoms. So here is what I was talking about. Obviously, if I bring two protons, one proton and one proton, and bring them closer from one another, yes, I have that interaction between them, but there is that nagging still non-zero and actually sizable amount of repulsion. If I bring two more that do the same thing, which are the neutrons, then the neutrons will attract each other, of course, first, and will attract the protons. So there is an attraction between the two neutrons. They will attract this to a proton, and this will attract that the other proton, and the other one will attract the other proton, and this one will attract. So now there is a net, far greater net. Because let's throw in numbers. Let's throw in numbers just for the sake of argument in here. Let's say, for example, this I calculated to be 10 Newton. Okay, it's more than that, but let's say for the case of argument that this is 10 Newton. And in here I have, let's say, for example, 8 Newton of repulsion. So 10 minus 8, I have a net still positive of 2 Newtons. Okay, 2 Newtons is good enough, but probably not too good enough for what needs to hold the helium atom. So now here is the problem. I have this and this. That is 8 Newton of repulsion. This and this is actually 10 Newton of attraction. This and this is 10 Newton of attraction. This and this is 10 Newton of attraction. This and this is actually another 10 Newton of attraction. And this is 10 Newton of attraction, plus this 2, which is another 10 Newton of attraction. Now I have 1, 2, I'm sorry, this is the same one. I counted it twice. This is the same one. So there is a 10 and 10, that is 20, 30, 40, 50 Newton, 50 minus that's still 8. So now I am in very good shape because I have what? 42 Newtons net, versus if I just put them together in here, where I have just a merely 2 Newton net, which is still positive, but not as positive if I just bring more 2 neutrons to the equation. Okay, you might be tempted to say, okay, how about if I bring a 3rd neutron to the problem? What happened? Well, the 3rd neutron in here becomes unstable. It doesn't really know which way it's going to go because it's asymmetrical. And then it's going to start moving things, shake things around just enough so that the whole thing becomes unstable. So helium 4 is actually stable. That's really why you need that many to keep them together. If you bring one, just one more, it's still asymmetrical, and the thing also still does not really look symmetrical. This is the perfect configuration in terms of, this is the most stable configuration for helium atom. Okay, I hope that this number gives you a sense of what we're talking about now. Because if you attempt to remove one neutron from the equation, the whole thing becomes kind of a problem. If you bring another one more than what you need, then it becomes a problem. If you bring just enough, you're in great shape. Okay. So that is basically what I was saying in here. So that net of 8 Newton that is repelling each other is going to be overpowered by the presence of these 2 neutrons. So neutrons are good people because they help things get together. Okay. They're good matchmakers, basically. Keep everything in balance. Here is the trouble that I was talking about in the beginning. In the case of a huge atom, big atom, this separation between this bunch of, for example, charges that are glued together there, that's fine, it's working there. And this side, for example, they become too far away. So we lose that additional bonding that existed in here. Okay, so this force becomes weaker and weaker and weaker by more and more nucleons. Yes, you're bringing more and more protons to keep things together, but now the protons themselves, I mean the neutrons to keep things together, but the neutrons themselves are not stable to begin with. They only live for about 15 minutes outside of the nucleus without transforming. I mean, this thing that I mentioned in the beginning, where is it? I think I mentioned it in here. Yeah, this thing lives only for about 15 minutes. I mean, half-lifetime of about 15 minutes. I mean, neutron by itself, if you put it outside by itself. So this thing in here is really becomes an issue when you have for a big atom in this case. So they're too far apart now, and this thing starts to falter because in this case, remember that nuclear force is not 80 Newton anymore when they are very far away. It's actually a lot less than 80 Newton. So this equation that I put in here for this side of 80 Newton, for example, I'm just throwing numbers in there so we get a sense of size. When they're too far away, it's actually not 8 Newton anymore. It's a lot less than that. It's probably 1 Newton at best. Okay, so now there is less nuclear fusion, nuclear force to fuse the thing together, but that's electrostatic force is still there, annoying, and it's big. So this then becomes completely, at some point becomes unstable. Okay. So that is really the essence of radioactivity. That is really why atoms now try to get rid of excess stuff to stay stable. I mean, nuclei starts to get rid of excess stuff to get stable. And now if you have a proton, I mean, a neutron that is sitting in there, not interacting with anybody, is going to flip and change on proton and get rid of that electron. And sometimes the atom itself, I mean, the nucleus itself is really not arranged correctly. So it just shifts enough. And that's what causes the release of the energy. So there are one of 3 ways: either eject a whole basically set of 4, like this ones, get rid of them. And that you have 2 protons and 2 neutrons, and that is your alpha decay. And now the atom the nucleus becomes more stable. Or a neutron that is sitting in here, for example, far away from everybody, is really going to be unstable. And it can stay there for on average for about half-life of 15 minutes. And then that will change color and becomes red, becomes a proton. I mean, yeah, becomes a proton, and get rid of that electron. This is your beta decay. Or the entire nucleus was actually not sitting correctly. So what it does in here, it shifts. And when it shifts, it does not emit any positive or negative charges. It leaves the number of charges the same, but get rid of that excess energy. It's like an earthquake, basically, when the plates move. Get rid of that energy in the form of gamma decay. So this is your 3 kinds of decay that we've been talking about that occur in nature. So it's just the nucleus trying to go back into a lower energy, basically, state. Okay. How long? And I mentioned already for the case of the neutron, for half the amount to decay, that is what we call half-life. This is a characteristic of the material, characteristic of the element in question. If I start, for example, with carbon-14, I can wait a little over 5,700 years for it to change on average. So if I start with 1 kilogram today, after 5,700 years, I will be left only with 500 grams in the form of carbon-14. Okay. How much carbon-12? I will have 12, actually I will have the other 500 grams. Okay. So that is basically in a nutshell what's going. If I wait another 5,700 and something years, this number changed from 500 grams to only 250 grams. Okay. For another 5,700 years. So now we're talking about 11,000 years. After another 5,700, 17,000 years, I would be left with only 125 grams. Okay. That is what is meant with it, with the half-life, basically, for a specific element. Each element has it. It can range from microsecond, from a millisecond, to billions of years, depending on the material, depending on the element. So it's really, and that's why they are useful for dating stuff, depending on the scale with which you would want to date things. Okay. So a certain isotope has a half-life of 1 day. This means the amount of that isotope remaining at the end of the 2 days will be, so half 1 day. So 1 day, we will lose 1/2. So this is how much we started with. After 1 day, this is how much we have. Now this amount, after the second day, so this is the daughter. This is the other one that we don't care for. Okay. This is the element itself, the isotope itself. Okay. And this is the previous isotope, the parent. So the parent in this case, I started with this amount. Half of it is gone. Half of it became whatever the other stuff is. So the other half now is still that same isotope. Another day, this half now will break into another half of a half, which is a quarter. And this becomes the daughter. Probably if the daughter is not also radioactive, this will add up to this daughter and becomes whatever that is. So now I'm left with a quarter of that element. Does this make sense? Yeah, correct. Thank you. The terminology daughter and parent is used in the case of radioactivity. So you have a parent to a daughter, and the daughter could be a parent too to another one, and so on and so forth. Okay, so this process can continue for a long, long time in here. Okay, so that is how the decay is in this case. Like for example, the example I started with carbon-14 becomes the parent. Carbon-12 is actually the daughter in this case. So here is an example. This is radium. So radium, after 1,620 years, if you start with 1 kilogram, you will be left with half a kilogram. After twice that much, you will be left with a quarter of it. After 4,800 years, you will be left with 1/8 of a kilogram. This never ends, though. You will always have traces of that element somewhere in there. Okay, we'll always have small amounts in there, even on the atomic scale in there. So the transmutation of elements, the changing of one element to another, natural events like natural transmutation, artificially in the lab too, you can do that too, actually. And this is actually what Mr. Rutherford did. Okay, this was using actually the radioactive materials. So in this case, what we have energetic neutrons come from the cosmic radiation on their own. They come to the nitrogen, which is nitrogen 14. Okay. Once they do, what they do in this case is they interact with it and they eject, in this case, a proton. So this is actually a proton. Oops. So this is a nuclear reaction that's going to give me a hydrogen atom, basically, in this case, because the proton will grab another electron somewhere and becomes hydrogen atom. And now you have carbon 14. So this is the process of how we make actually carbon 14 in the cosmic, in the atmosphere. It's made naturally by itself, okay? So in this case, that's how we end up with carbon 14, which is not stable by itself. It actually decays into carbon 12. So you have started with an element which was nitrogen, and now you end up with carbon, and actually hydrogen too. And alpha decay by itself, for example, also is transmutation. For example, uranium-238 becomes thorium-234, okay, plus helium atom. So in this case, you have two materials that are made up of the original one, okay? So you ask me, where is the parent, where is the daughter? Here is the parent. Here is the daughter. This is actually the alpha decay, okay? I mentioned the fact that the number, the atomic number, actually is going to increase by 1 in the beta decay. That's very important that you guys need to remember that, because atoms in this case move in the periodic table. Here is the thing: gamma emission from a nucleus, no change in mass number, no change in atomic number. So what happened in here? But that question way back, if you guys remember it. So I remember that I told you guys that the element may or may not change. So that is actually the correct answer to D, because in this case, you start, for example, with the lead that is not stable, and now you become with lead that is stable plus gamma radiation. So in this case, the parent is still lead, the daughter is still lead, and this is just a decay, which is a gamma decay. And except now you get rid of that excess energy. Usually the star goes after or before, yes. Okay. For lead to indicate that it was actually unstable and now it became stable. Okay. So this is an example of where the element is still lead. It has the same Z number, the same protons, and the same A number, which is the same protons plus neutrons. Okay, both of them are the same, so it's the same element. Chemically speaking, the same element. Again, the half-life, how are we doing on time? So again, I talked about the Rutherford. Basically, what he did was he took helium ions, which is alpha particles from radioactive materials, and transformed nitrogen to oxygen, actually, plus protons. And he was able to find traces of both of them in the nuclear. So that was actually proof of that you can do it artificially. You can make it artificially. And like this process that I was talking about, actually, this is done in nature. It actually happens in the atmosphere due to the cosmic radiation. This one in here. But now we do this far more often in nuclear accelerators. We have all kinds of nuclear reactions that we can produce. So this is an induced nuclear reaction. Okay, that's how we made most of the elements, by the way, in the past the 92 elements, past the 92 elements occurring in nature on their own. So when an element ejects an alpha particle, the atomic number, which is Z, the number of protons, that is, that's what we mean by the atomic number, resulting reduces by 2. Of course, it's going to go by 2. It goes from Z to Z minus 2 because you lost 2 protons. So the element went in the periodic table from which location? 2 steps back to the left, okay? In the case of the alpha particles, is going to increase by 1. Actually, it moves to the right by 1. So the correct answer is this one. So this is Z, going to Z plus 1. What happened in here in this case? You have a neutron became a proton. So whatever you started with in the number of protons, you add to them this neutron that has changed to a proton, obviously emitting the electron that left the whole nucleus. Okay, that's fun. You have an element, certain elements emits an alpha particle. So it emits an alpha particle. It was sitting in here. It emits an alpha particle. So after the alpha particle is gone, now it sits at Z minus 2. We just said that. It lost 2 protons in the process. And its products, the daughter elements, then emit 2 beta particles. So this one now emits a beta particle 1, and now it's going to add to it 1. So whatever it was, Z minus 2, add to it 1. So this is 1 beta. Then it does another one, 2 beta particles. So it's going to add to it another one with another beta particle. So Z minus 2 plus 1 plus 1 plus 1, that is actually back to Z. So its atomic number changes by an amount that is exactly 0. It does not change. So it went to the left 2 steps. So this is what happened to it. It went 2 steps basically, because it did the alpha particle. Then it went back by 1 beta, and it went back by another 1 beta. So it went back to the original element. So it never moved from the periodic table. Again, radiometric dating used by plants for plants and animals based upon the ratio of carbon-12 to carbon-14 because of the half-life of carbon, which is 5,760 years. Obviously, this number is not an exact method because the way that carbon is produced, carbon-14 is produced in the atmosphere is not fixed year to year, but it's on average, it's a good number to use in here to come up with at least an approximate age of the plant, okay? Okay, so we use that for living organisms, but non-living organisms, for example, we use uranium. Uranium, we have 2 isotopes, uranium-235, which is about 700 million years. So if you're looking for something of the order of millions of years and probably 500 million years or even 800 million years or something like that, look for how much uranium-235 you have in there versus how much lead-207 you have in the material. Then you can find its age in millions of years, okay, or at least hundreds of millions of years, give or take few million years, 10 or 20 million years, because again, this thing is, there is that error in the calculation still. Now, if you want age of the order of billions of years, then in this case, you use uranium-238, because uranium-238 versus lead-206 has a half-life of 4.5 basically billion years, okay? So an archaeological dig uncovers an ancient spear whose wooden handle contains 1/8 the radioactive carbon of a fresh piece of wood. About how old is the spear? Okay, 1/8. So this is carbon-14 when we started the process, okay? If we wait 5,760 years, we will be left with half of the carbon-14. This is carbon-14, okay? And if we wait another 5,760 years for a total of how much? 0, 12, 15, 11,520 years, this half breaks by another half for a total of 1/4 of carbon-14, okay? So I need another 5,760 years, which gives me 0, 8, 12, 17,280 years to lose half of a quarter, which makes it an eighth of carbon-14. So the correct answer is this one, B. Does this make sense? Obviously, this is not an exact thing, okay? About this much, okay? So don't take me exactly and say, oh, maybe it's not 17,280 years, maybe it's 17,279 years, give and take a few, a few hundred years, okay? Okay, the nuclear fission again. Once a neutron in here is trapped by uranium-235, for example, the uranium-235 now is shaken enough so that the parts of it become too far. And it's going to break into two different elements. For example, krypton and what is this one? Barium. That is a possibility for it. And then in the process, it ejects 3 more neutrons. So this is actually could start new fission. And that's exactly what we use it for the chain reactions. So again, when the neutron hits the collides with a nucleus, in this case, uranium-235, these parts become too far apart, and then the electrostatic forces will take over. And the elements that come off of it have tremendous amount of kinetic energy. That is basically how the nuclear bomb is, or nuclear reactor uses. So now the products of this are these neutrons that on their own can go and trigger more nuclear reactions, which in turn, so each one of them can give you up to 3. So those 3 can trigger up to 3 more. And so basically 3 times 3 is 9. And those 9 can trigger each and every one of them 3 on its own, and so on and so forth. So this can become a chain reaction. So this is what we mean by chain reaction. A critical mass is the minimum amount of fissionable material in the reactor or nuclear bomb that will sustain a nuclear reaction. Because if you don't have a lot of uranium-235 in this case, a lot of these neutrons will just go basically and fly away and don't interact whatsoever with anything. So in this case, the nuclear reaction is not sustained. But if you have at least a certain minimum of it, that each and every one of these neutrons that is ejected from the nuclear reaction will go and at least trigger another nuclear reaction, now you have a sustained chain reaction. So there is a critical mass that you can use for that, okay? A mass large enough to sustain fission. So that is exactly what this critical mass is. It can result in an enormous explosion, namely the nuclear bomb. Obviously, 235, 238, 239, different isotopes, because they have the same Z number, but different A number. The same atomic number, but a different mass number because they have different neutrons. Okay, this one has more neutrons, has 1 more neutron than uranium-238, which has 3 more than the uranium-235. Okay. Mr. Einstein discovered the law that basically E equals to mc squared, and that can explain a lot of what's happening inside the nucleus. And that missing energy is exactly the energy needed to bind the nucleus together. So this is a famous equation that Mr. Einstein has basically derived from his assumptions about the relativity. Of course, the more mass you have, the more energy you have, because C is just a constant. C squared is just what? 300 million squared. Oh man, this is a big number. This is 9 followed by, how many in here I have? 16 zeros. Can you read this number? I can't. It's a big number, okay? Yeah, it's 9 times 10 to the power 16 meter per squared per second squared. It's a big number. So this is basically what it is. So the more mass you have, the more energy you have. And this is usually for the bonding of the different elements. As a matter of fact, if you look inside the proton itself, or inside the neutron itself, it's made up of tinier particles called quarks. But those particles, if you add their masses, they don't amount at all. They are very tiny compared to the mass of the proton and neutron. Most of the mass of those particles, which are supermassive, is actually pure energy. That is really what that is. So the mass for its vast majority now can be explained just by being pure energy, basically concentrated in a single point in space. That's all. So again, the missing mass can explain the bonding of different elements. The mass difference is called, okay? The mass, the nuclear mass and the atomic number, they're proportional to one another, almost like a line, but not exactly. Almost line. So the difference is actually that bonding. The difference is this amount. That is what the difference is, okay? In other words, I bring a proton, by itself has this much mass. I bring another proton, put it next to it. I should have twice as much. I don't have twice as much. I have slightly less than twice as much, okay? If I bring two neutrons next to one another, I know how much the neutron is, and I know how much the other neutron is, and I know how much the proton is, and I know how much the other proton is. When I put them together, I find that it's not exactly the sum of all of four of them. It's actually, there is a slight difference, and that slight difference is what went to keep them together, to fuse them together. We need to finish. I think we still have quite a few stuff in here. So again, this question is related to that. Here is a point in here that you need to remember. The mass per nucleon, which is a different story than the mass of a nucleon or the atomic mass. Okay, so you have to remember the two concepts. That means I take a mass of an element and divide it by the number of protons it has, or the number of nucleons it has. Okay, that gives me how much energy really went into binding. The less of that number, that means the more went to that binding, okay? The highest number I have is the hydrogen by itself, because it's not bound to anything. It's a proton floating by itself. Since I know how much the mass of a proton, I know that ratio of how much mass for that proton is. Now, if I bring another proton, as I was saying, and if I find how much the whole mass divided by 2, I find that the mass is actually less. And as I go through this curve, it's less and less and less, and it bottoms in iron. Then after that, it starts to increase more and more and more. So here is the idea for the whole business in here for the next slides. If somehow I break this nucleus, I will end up with two parts that somehow will land in here, okay? In terms of the ratio of their mass per nucleon. And then energy, plus energy. Where is that plus energy coming from? Because this was sitting at a higher point than both elements in here. So these elements, when they combined to make this one, they must have lost energy to get together. And that energy what went to make them together. So if I do fission, which is this process, fission, I will end up with an energy. But I cannot do fission past the point of iron, because then I'm going to go up then, because I need to put more energy to put things together. So what I do in this case, if I take this element and combine it with this element, I probably will end up with a new element that sits in here. And I will end up with an excess of energy, because when they combine, they get rid of that excess energy, and the ratio of the energy per nucleon drops. And I will gain that excess now. That is plus energy too. So I'll gain energy if I go this way. I'll gain energy if I go this way. This is fusion though. Up to iron. I cannot combine stuff now and get more energy out of them. Actually, I need to put energy in here. So in this case, it's actually an endothermic reaction. In a sense, it produces, I'm sorry, exothermic reaction because it produces energy. And in this case, also, it's an exothermic reaction, nuclear reaction, because it produces energy. If I go in the opposite direction, I have to supply energy to it for it to happen. So this is actually an endothermic reaction. So I need to put energy in order to go up. I also need to put energy in order to go up. So iron sits at the bottom of everything. It's the most, or at least the least mass per nucleon. That means the most amount of energy already went to making iron. You cannot make more than iron through fusion, or you cannot break elements together and gain more energy up to iron. Iron sits at the bottom. So this is really explains all the slides that are coming down from 52 all the way to whatever that last number of the slide says. In which of this element does the proton have the greatest mass? Of course, hydrogen, okay? Iron is actually the least. And that's the next question. Which element has the least mass? Of course, iron, okay? So again, this is what I was talking about earlier. So uranium-235, when it splits by gaining that proton, neutron. So in this case, it's going to go into two fragments, okay? And barium and krypton in this case, both of them sit at a lower level in their ratio mass per proton. So in this case, what's going on in this case is that we gain that energy. So that is energy that we're going to gain, okay? And if we do the opposite in here, in this case, for example, we take two isotopes of hydrogen in this case, and if we use them together to make helium, then in this case, we also gain energy. Because the mass per proton is less now, so where did that energy go? We gain it in the form of energy, okay? Same thing in this case too. So we have nuclear fusion this way. Well, you have nuclear fission this way, up to iron on both sides. Okay, this is the entire chapter today. And we're due for another exam, and the other exam is actually going to be postponed to after the spring break. The reason why I'm saying that is because I myself, I will be on campus at that time with other students doing exams. So you guys will have your exam online, okay? So that's basically on the week after spring break. So I should post the exam review, hopefully by next week. So that you start it immediately before you go into your spring break. And then you submit it immediately after spring break. And then we will do the exam on that day, similar to the first exam where during the exam, since I'm going to be part of the day on campus, so I will not be available, but during the exam itself, I will have access to a computer, answering any of your questions. If there is a problem or anything like that, you still have time to submit the exam later on. But you have to understand that sometimes I will not be able to answer immediately. There will be a cutoff, though, for when I can reply to your answers. So do not leave it to the last 2 hours or something and ask question that, hey, there is a problem with this exam, because even if there is a problem by then, it's too late for me to send a notification to everybody else saying, hey, there is a problem in here. Too late. So you have to deal with it. Hopefully you start the exam as soon as possible. So that's the only thing I'm saying right now. So I'll see you guys next week. And that's it. Let me stop recording first.